Okay, so we're going to start off today with section 1.2, exponents and scientific notation. Can we get the lights, please? Very good, thank you. So today we're going to discuss a number of rules for exponents, and then we'll finish up with scientific notation. So the very first rule that we want to discuss is the product rule. So using the product rule for exponents. So the product rule for exponents says that if I have an exponential expression, x to the m power times x to the n power, that's equal to x to the m plus n power. So when we multiply two factors together that have the same base, in this case our base is x, and different exponents, we add those exponents together, okay? So let's do an example of that. Example 1. We want to simplify x to the third power times x to the fourth power. So what does the product rule, what does the product rule say that we should do in this case? We should add the exponents. So x to the third times x to the fourth becomes x to the 3 plus 4, which is x to the 7th. Any questions about that?
What's the situation where you multiply the exponents?
We will get to that in a bit. For sure. That's a good question. Let's do another. Example 2. This time, our base is not a variable, but a number. So 3 squared times 3 to the third power. I'll move up so you can see it in the back. How can we simplify that?
Well, exponents come first in order of operations, so first we would add those two together.
So we can add the exponents together because we have the same base. So that's 3 to the 2 plus 3, which is 3 to the 5th. And what is 3 to the 5th power?
3 times 3 is 9, times 3 is 27. Times 3, it's too early.
Times 3 is 81. 81. Times 3 is?
3 times 81, 81. Take the 1 out.
This is a good place for you to stop and plug it into your calculator. 3 to the 5th power.
243.
243.
It's called the mental math trick, you know.
Okay, so this is also a good point for me to stop and say, you need to have your calculators out. And your phone calculators probably aren't sufficient. But if that's all you have, that will work for today.
No, I don't have my calculator. I don't know where it went. Let me see. Oh, yeah. Thank you. I appreciate it.
Anyone that wants to borrow a calculator, now's a good time to come get one. Don't worry. It's all right. I got more.
It's all nice and prepackaged. It's crazy. Yeah, I got you. You know why he called me Joe? You know? Ooh. Scary.
Well, it's official now. I have to use consent forms. We set a name.
Oh.
I had avoided it for the first 3 minutes. Oh well.
Oh well.
I think we'll make it. Let's do another example. Example 3, we have t to the 5th times t to the 8th power. And I'm going to pause for a minute and give you an opportunity to work on this example on your own for just a moment.
T to 13. Scary. People don't even really need to wear wires nowadays. You just wear one of those. Like the phrase wearing a wire, it's kind of outdated.
A little bit. So, t to the 5th times t to the 8th.
Turn it on 80 so I can dry my hair more.
Okay, so our first step is to add the exponents, right? What do we get?
13.
T to the 5 plus 8, which is t to the 13th power. Any questions about how we use the product rule? Okay, let's go to a new rule. Using the quotient rule of exponents. So the quotient rule of exponents says that if I have a quotient, y to the m over y to the n, again, we have the same base, different exponents. What this says is that I subtract the exponents. Very similar to the product rule, and that's because multiplication and division are very similar operations. So we get y to the m minus n power.
So m is always going to be first?
The numerator's power will always be first, yes. And the way we'll discuss that in the future is that the denominator, the exponent in the denominator is what we subtract, because that would be a negative exponent if it were written in the numerator. And this is true as long as m is bigger than n. So if we end up with a negative exponent, we would put that positive exponent in the denominator. Questions about that rule? Okay, so again, we're going to subtract the exponents. Let's do an example. Example number 4. And we want to simplify t to the 23rd power divided by t to the 15th power. Someone tell me what to do.
23 minus 15.
We're going to put t to the 23 minus 15. And what rule is that?
Quotient.
It's the quotient rule of exponents. And 23 minus 15 is 8. So we end up with t to the 8th power. Does anyone have any thoughts on that? Does anyone not see where we got that? Okay, let's do another. Again, I'm going to bring up specific numbers. We want to simplify. -3 to the 6th power divided by -3 to the 1 power. Can I have that sign-in sheet back, please?
Will it equal out to 1, 1 to the 5th power?
So what is our base? What's our base in this case?
-3 divided by
So
-3.
so we don't actually do the -3 divided by -3 first. Remember, we do exponents
that's
first.
right, yeah.
So we're going to have to deal with those. So
Yeah.
we can do 6 minus 1. So we'll have -3 to the 6 minus 1. And what is 6 minus 1? 5. So we'll have -3 to the 5th power. And what is -3 to the 5th power? -243. And why is it -243? Because we have an odd number of factors. So we would have 5 factors of -3. So 5 negative numbers multiplied together gives us a negative. If we'd had an even number, it would have been positive, but because we have a 5, it is negative.
Well, why don't we also like do the division side with the whole numbers, not the exponents?
Explain that to me.
So we did the 6 minus 1 with the exponents, right?
Mm-hmm.
Why wouldn't we also do the division after we do the exponents? Because is that because the exponents come first and like?
So once we use the quotient rule and subtract the exponents, there's not division anymore.
Okay.
So it's just the -3.
Okay.
Good question. Any other questions? Comments, concerns, criticisms? What are y'all doing back there?
She was teaching me about the calculator.
Very good. Good. All right. Our next rule. Anyone have a preference for the color I write with?
No.
Purple? We like purple? Okay. That's good with me. Using the power rule. Of exponents. So we're on the previous examples or the previous rules, I've gone to examples after I told you the rule. This time we're going to do it the other way and do an example first. Example 6, we want to simplify x squared raised to the 3rd power. Now in this case, we have something raised to a power that's then raised to another power. And Joe, can I call you Joe?
Yeah.
Are we close enough that I can do that?
Yes, sir.
Okay.
Anybody can call me Joe.
Okay, well I just wanted to make
There's
sure.
no prerequisite.
Okay. That makes me feel a little sadder though, but okay, just because anybody gets that privilege. So this gets to your point a minute ago where you said, when would we multiply?
Yeah.
This is it. When we have a power raised to a power, that's when we'll multiply those exponents. And here's why. Tell me if you think this is true. Is x squared raised to the 3rd power the same as x squared times x squared times x squared? And why is that true? Because we have x squared raised to the 3rd power, the exponent means that we have 3 different factors of x squared. That's what it means to raise something to a power. Well, x squared is x times x, right? Do you agree with that? So that means we'll have x times x times x times x times x times x. How many distinct factors of x do we have?
6.
We have 6. So in other words, we can add these exponents, 2 plus 2 plus 2, which is 6. Or if we had this power rule, we could have just started here and multiplied 3 times 2. And that's why the power rule works. So, in general, and I'll define that formally in a moment, so if we have something like a to the m raised to the n power, that simplifies to a to the m times n. So I've sort of eased you into it. We've done some rules. Now we're going to start with formally defining things. Yes?
This is rule called.
It is the power rule of exponents.
Power.
And I was actually just about to write it again.
There's a trash book that has about like 48 laws over it. People really overrated. Honestly hate hearing about it.
So let's do a definition. So the power rule of exponents is what we're defining, states that for any, that looks like Neil and not real, any real number a and positive integers m and n, that a to the m quantity raised to the n power is equal to a to the m times n. That is the power rule of exponents. Does anyone have any thoughts? Any questions so far? Hearing no opposition, we will do example number 7. And in example number 7, again, our instructions are to simplify. And we have x squared quantity raised to the 7th power. What does the power rule tell us we need to do here? Multiply what?
2 times 7.
Multiply 2 times 7, which are the exponents. So we will get x to the 2 times 7, and x to the 2 times 7 is x to the 14th power. How do we feel so far? Confident? Happy? Excited? Ready to go? Not peppy enough. It's not 8 o'clock anymore. It's almost 8:30.
Oh.
All right, let's do another. Since you're so excited about the day, I have negative g to the 4th power, and I have that quantity raised to the 4th power.
Well, groups first, right?
So this is going to fall under the power rule. So we have this negative g thing, whatever's inside those parentheses raised to the 4th power. So we take the power that's raised to a power and multiply those exponents together. So that stuff, negative g, is raised to the 4 times 4 power. And what's 4 times 4? So we get negative g to the 16th power. Do we have an odd or even number of factors? We have an even number of factors. So our result will be positive. Very good. So what is our final simplification? G to the 16th. Very good.
That's crazy, yo.
Oh, you just wait. You just wait.
I thought you wanted me to be us to be exciting, though.
I don't know. The exciting part is the next rule.
Oh, scary. Shivering temper. You know, Davy Jones' locker or whatever.
All right. Switching colors because this one is going to be so exciting to you.
Yellow.
No, yellow's too bright.
Exactly.
Yellow.
Can you alternate between every color for every letter?
Oh no, no, I
That's too
cannot.
much work. Oh yeah, the way he has to select that, that's a no.
Well, I can put multiple colors up there and just tap between
Oh.
them, so it wouldn't be that bad. But I'm going to use green, and then we'll get something more yellowish in the near future. Okay. Using the 0 exponent
Using your secret
rule of exponents. The 0 exponent rule of exponents. That's a lot to say. So if, oops, that switched colors on me accidentally. So if m is equal to n, let's say they're equal to 2. Doesn't matter what we choose, but let's say they're equal. And I have t to the m power divided by t to the n power. What does that give us?
T minus, T m minus n.
It will be that, but we know that m and n have specific values in this case, which is 2. So we'll have t squared over t squared. Well, that, as Erica said, is t to the 2 minus 2. What's 2 minus 2? That's t to the 0. Well, if we look back at this step, this is a number. T squared is a number. Do you agree with that? Divided by itself. What's a number divided by itself? Try again.
one.
It's 1. A number divided by itself is 1. So t to the 0 power is equal to 1. So any non-zero number, as long as t is not 0, and you raise it to the 0 power, you get 1. So let's define that. So the keeps changing to the highlighter. The 0 exponent rule of exponents states that for any non-zero real number a, that a to the 0 power is equal to 1. A to the 0 power is equal to 1. Any questions? Just a few people writing. I'll give you just a second to get caught up. Are we ready for an example?
No, we're ready for an exam.
Oh, well, I can do that. I think I've got one here.
Bet. No, I'm playing.
No, it's just a sign.
Okay. Whoa, don't.
Example, we're on 9, right? Example 9. I have w to the 8th power divided by w to the 8th power. You're going to be very surprised at what the result is here, because this is a very shocking property. If we want to simplify, what do we get?
I have nothing. 0.
W to the 0 power. Well, let's do 8 minus 8 first, which is w to the 0. And any non-zero number to the 0 power is... Did I hear somebody say 0?
1.
Let's say it again. Any non-zero number raised to the 0 power is...
1.
1. What is it? It's 1.
1.
Celebrate. Celebrate the 1.
Celebrate 1. His birthday.
Any questions about the 0 exponent rule of exponents?
So if the top number is like -8, still take -8 minus 8.
So it would be -8. If you had the same exponent in numerator and denominator, is that what you're saying? It would be -8 minus a -8. So minusing. Subtracting a negative number turns that number to a positive. So it would be -8 plus 8, which would still be 0. Good question. Are there other questions? I'm going to make y'all play musical chairs, make you move around. Being too quiet. All right, new rule. Using the negative rule of exponents. So if we have that m is less than n, those are going to be our two exponents. We haven't talked about working with inequalities yet, but if you subtract n from both sides, of that inequality, you would end up with m minus n less than 0. What does that mean? That means that when we subtract the exponents, you end up with a number less than 0. And a number less than 0, we have a special name for that, and it is?
A negative.
It's a negative. Okay? So let's try, maybe not an example, but a consider. H to the 3rd power over h to the 5th power. We can still use the quotient rule, or a variation of it. What would we do with those exponents?
Will you flip them around?
We won't flip them around, but we will still subtract. So we'll have h to the 3 minus 5, which gives us a negative 2.
If the number equals 0, right? After it's simplified?
No, not yet. Hold off on that thought. So we'll have h to the negative 2. Now, typically we don't write final answers with negative exponents. Okay, so don't get into a habit of doing that. Let's take another look at that same expression, h to the 3rd over h to the 5th. We're going to look at it a little bit differently. In the numerator, how many factors of h do we have? So we have h times h times h. And how many do we have in the denominator? We have 5.
So do we cancel out 3 of them?
So we can cancel out 3 pairs. We can cancel out a pair in the numerator and denominator, a pair in the numerator and denominator, and a pair in the numerator and denominator. So how many are we left with in that denominator? We have 2 factors of h in the bottom, which is 1 over h squared. So since we've looked at this 2 different ways, and we got 2 different ways of looking at the answer, h to the negative 2 power is the same as 1 over h squared. So let's write that. H to the negative 2 is equal to 1 over h squared. And we'll formalize that negative rule of exponents here in just a moment. But basically what it says is that if I have something raised to a negative power, that I flip it, that I put it from the numerator to denominator and change the exponent to a positive. Does everyone see where that's coming from? Do we have any questions?
And that's only because you can't have an exponent as a negative.
We don't want, right, we don't want to put negative exponents in our final answers. Correct. See, just a few people writing. We'll take just a moment here.
You couldn't even ban me from Costco.
Did somebody try?
Nah,
No.
just couldn't.
What about Sam's?
I would purposefully get banned from there.
Really?
I don't know.
They have a hot dog and soda combo for like $149.
Yeah, but like, why? That could just.
That's fair.
You have to be a member now.
Huh?
You have to be a member now.
You do have to be a member, that's
Yeah.
true.
You used to not.
Not only that, you can't order at the counter anymore. You have to order through the app.
What?
That's how they ensure you're a member, instead of having to scan the barcode.
Yep, they know for sure that you're a member that way. Anyway,
Sam's Club sounds like some sort of gang or something. You gotta be a member, like.
Sam's
something-
gang.
Or like a cult. Like it's not a grocery store.
All right. So definition. For any non-zero real number, A, any non-zero real number A, and a natural number N, the negative rule of exponents states that a to the negative n power is equal to 1 over a to the n power, which is exactly what I just told you before. Now remember that a natural number is what kind of number? What does that look like?
0, 1, 2, 3.
So a natural number is 1, 2, 3, 4, and so on. Positive whole numbers. So our A, our real number, is anything but 0, and our exponent is a positive whole number. So negative n is definitely negative. That's what we're forcing to happen. Any questions to this point? Because we're about to do an example. All right, example 10. We want to simplify negative 5 times t to the third power raised to the fourth over negative 5t to the third power raised to the eighth power. So, what rule do we want to use? What rule do we want to use first? So I think that I want to start on the outside and subtract those exponents, right? And why would I want to do that? I have some people looking at me incredulously like, why would you do that? Why would I do that?
Because I don't really know, actually.
Well, we really don't have any way to deal with it other than that. Because we don't have what's called the power of a product rule, which is the next thing we talk about, the only way we can deal with this is to say that this is just a number. We don't know what it is. But this is something that's non-zero, and we have these exponents, so we can subtract them, right? So it doesn't matter what it is. It's negative 5t to the third. We're just going to leave that. It's just stuff. It doesn't really matter. It could be anything except 0. And it's to the 4 minus 8. Okay? So what does that give us? To the negative 4 power. What does the negative exponent rule tell us?
That we have to rewrite it.
And how do we rewrite it?
We
1 over negative 5t to the third raised to the 4th power. I like it. I see some confidence there. You just don't want to be called on, right?
Yeah.
You don't want me to directly look at you and say, hey, what's the answer? So now we do have something that we can work with, right? What can we do?
well, we can do the power. What's that rule called? The power rule.
So we can put the exponent on the inside.
Yeah.
So this is a preview of the next rule. This next part is. And that next rule that we'll get in just a moment says that I can take this exponent and put it inside with both of those factors. So that's negative 5 to the 4th power times t to the third to the 4th power. So we're still going to have the 1 over stuff, right? The 1 over stuff. And negative 5 to the 4th power is not negative 20. Remember, we're raising to a power. So in your calculator, put in parentheses. Be sure to use parentheses since it's a negative. Negative 5, close the parentheses, raise that to the 4th power. Did you put it in parentheses? You have to put it in parentheses. It's a positive 625. Positive 625. And the reason we know it's positive is because we have an even number of factors, right? Okay. And then t to the 3 times 4 is t to the 12th power. Now, Again, we don't have the rule to do this step yet, but we will on the next slide. Any questions? Comments, concerns, criticisms, donations?
Instead of donation, you can do compliments, and you can receive or give you.
Compliments? I could add that in.
Take out donations.
Because what?
Because it's a deed.
Mm,
Compliments. Go with the C's.
yeah.
You're welcome.
I've always been told to avoid annoying alliterations, though.
Who told you? No.
The allegory allocator.
Yeah. All right. Let's talk about the power of a product. We want to find the power of a product. So we want to consider P times Q raised to the third power. What does that mean by definition? How many factors of P times Q do we have? We have 3. We have P times Q times P times Q times P times Q. Do you know any properties of multiplication? By name, maybe?
I don't know any by name. I know it doesn't matter what order you do it.
It doesn't matter what order you do multiplication in. Does anyone know what that's called? My former students, I'm disappointed in you. What are they called? When you move the order of your multiplication, that's called the commutative property of multiplication. The commutative property. It means you can commute the numbers. They can move from place to place. Okay? Another property of multiplication that we get is that you can reassociate them in any order you want. So what that means is we can drop those parentheses. So let's drop the parentheses first, and we'll get P times Q times P times Q times P times Q. No parentheses. That's the associative property that we're using. After we use the associative property, then we can use the commutative property and change the order. Why do I care about changing the order? Well, I want to put all of my P's together and all of my Q's together. I want to literally mind my P's and Q's. Okay, tough crowd. So I'll put the P's together. How many factors of P do we have? P times P, like 3 P's in a pod,
That is not good enough.
times Q times Q times Q.
And this one is for commutative.
That's the commutative property. So, now we have how many factors of P? We have 3 factors of P. So how could we write that as an exponent? P to the third power times Q to the third. And this gives us the basis for the rule that we're about to do, which is the power of a product rule. Because what this really said was that this exponent in the very beginning,
Couldn't you just distribute it?
we could distribute to both factors. And that's what the rule says. So let's do a definition. Oops. For any real numbers, A and B, and any integer n, the power of a product rule states that A times B, a product, that's what a product is, two things multiplied together, right? Raised to the n power, that entire product raised to a power, is equal to each of the factors in the product, so A and B, each raised to the n power. A to the n times B to the n. Any questions? Questions doesn't start with a C. It does have the same sound, doesn't it? Yeah. So it would still be alliterative. Okay, example 11. We want to simplify 2 times t quantity raised to the 15th power. What does the power of a product rule say we can do in this example? We can distribute what? We can distribute the exponents to what? Each of the factors, 2 and t. So what do we get? 2 to the 15th times t to the 15th. Are we done?
No.
Why are we not done?
You have to simplify.
We need to simplify that 2 to the 15th power. And what does 2 to the 15th give us? It's a big number, right?
Sixty-eight.
32,768 times t to the 15th power. Any questions about that one? Okay, let's do one more example about the power of a product. We want to simplify g squared times h to the 3rd power raised to the 5th power. And I'm going to give you just a couple minutes to work on that on your own. Okay. What can we do to simplify this?
Distribute and then multiply.
We can distribute the exponent, that 5 inside to each of the factors. So we get our first factor, which is g squared raised to the 5th power. Yes? Times what? H to the 3rd raised to the 5th power. Okay, what do we get from here?
G raised to the 10th power multiplied by h raised to the 15th.
G to the 10th, that's 2 times 5 times h to the 3 times 5, which is 15. Did anyone get anything different from that? Okay, we're down to our last rule of this section. And that is the power of a quotient. The power of a quotient. So, I want us to consider the expression e to the negative 2 power times f squared raised to the 7th power. And we're going to consider this 2 different ways. Again, the first way that we know how to consider this is to use the power of a product, right? We can take that exponent, which is 7, and bring it into each of the factors, right? Yes. Up and down for yes, side to side for no. Yes. Katie, you good in the back? I can't see you. Okay, just checking. So we'll have e to the negative 2 times what? E to the negative 2 times 7 times f to the 2 times 7. And then when we multiply those exponents together, what do we get?
E to the negative 14.
E to the negative 14 times
F to the positive 14.
f to the positive 14. So we have a negative exponent. We can't leave that in our final answer. So yes, you could write that particular factor as 1 over e to the 14th. But since we already have this f to the 14th in the numerator, we can just leave that as our numerator. So I'm following along with your instructions and just keeping the f over 14 or f to the 14 over e to the 14.
So then if we left the f to the 14 in the bottom, we didn't have to worry about the e, or you still have to worry?
So the f to the 14 has to stay in the numerator because it's got a positive exponent. Good question. Now, because we have a way to deal with negative exponents, we're going to consider this a different way. E to the negative 2 times f to the 2 raised to the 7th. We can actually deal with that e to the negative 2 in our first step. And we can get f squared over e to the 2 power. Because those two things are the same, right? We're not doing the operation first. We're just changing it to a different view, bless you, of what e to the negative 2 is, right? We're still going to go through the same process with power of a product. But we have f squared over e squared raised to the 7th power. Do you agree that this is the same thing as that. Have I changed the value of the expression? No, we have not. But now, in this format, we can distribute that 7 into each part. And so I'll get f to the 2 times 7 over e to the 2 times 7, which gives us f to the 14th over e to the 14th. So in summary, we get the same thing either way, right?
The exponents don't have to be the same to do that, like, because it's -2 and 2, but what if it was like -3 and 2? It could still.
It would be just fine. The exponents do not have to be the same. It's the fact that we have a negative exponent that we can move to the denominator. That's the only thing that has to be visible here. Very good question. All right, I'm going to switch to my bubblegum pink color as we do our last rule. What? No yellow today. Maybe we'll go to dark mode tomorrow. Who knows?
Yellow and white is
So for any real numbers, A and B, and any natural number n, the power of a quotient rule states that if I have a quotient, a over b, raised to the n power, then I can still distribute that exponent to the inside, and we get a to the n over b to the n. It's too early to be yawning, man. Example 13. We want to simplify -1 over w cubed. I'm going to rewrite that 3. There we go. Raised to the 35th power. What does the power of a quotient rule tell us? I'm going to underline that in the definition. We can distribute the 35 power to the factors in the top and the bottom. So what do we get? -1 to the 35th divided by w to the 3rd raised to the 35th. Now, 1 and -1 have this really cool property that when you raise them to a power, that it's either 1 or -1, right? Really, -1's the one that has the property. Because we have an odd number of factors, what does the numerator become? Just -1. Right? And then w to the 3rd raised to the 35, what do we do with those exponents? We multiply the 3 times 35. What is 3 times 35? 105. So our final answer is negative 1 over w to the 105.
If it would have been a positive one, would you have still multiplied it like that? And
We would have still gone to the 35th power, but 1 to any positive power is going to give us 1. Good question. Are there any other questions? Okay, now that we have all of these new rules in our toolbox, let's use some of them together for simplifying exponential expressions. And this is example 14. So we want to simplify and write with positive exponents only. And our expression is x to the 8th power times x to the negative 12th power times x. So what can I do first? We want to get rid of that negative exponent, right? So we can do that by moving it to the denominator. So I can rewrite as x to the 8th times x, and then I'll just put my x to the 12th in the denominator. Any questions as to how we got that? We moved the x to the negative 12 to the bottom and made the exponent positive. Okay, now in the numerator we have x to the 8th times x. What does that give us? What's the exponent on just x? It's 1. So we get x to the 8 plus 1 over x to the 12. What's x to the 8 plus 1? X to the 9 over x to the 12. And now we have the quotient, right? Which we can subtract the exponents. That's x to the 9 minus 12. And 9 minus 12 is negative 3. Are we done?
No.
Why not?
I'll do a negative number.
We can't have a negative exponent in our final answer. So what can we do with that exponent? We'll move that entire factor to the denominator to get 1 over x to the 3rd. Very good.
Couldn't you have just added those, moved the x around, added those together, and added that with the 12, and then just done that?
Could we have just added the exponents right here in this step? So 8 plus a negative 12 plus 1, absolutely we could have done that. If that works better in your brain, do it that way. Any questions, comments, concerns, criticisms, compliments?
Complaints?
Criticisms covers that.
Oh, yeah, that is true.
Okay,
Commanders.
our last topic of today. Our last topic of today is scientific notation. Using scientific notation. And we'll start with a definition. So a number is written in scientific notation a number is written in scientific notation if it is in the form a times 10 to the n power. So we have a number times 10 to some positive power where the absolute value of a is greater than or equal to 1 and less than 10. And n is an integer. So our power on 10 doesn't have to be positive. I may have said that, but what I mean to say is 10 can be any integer power. And a has to be between 1 and 10. Strictly less than 10 and can be equal to 1. What does that mean for practical purposes? It means that this part that you have times 10 to some power has to be a number that has 1 digit to the left of the decimal. If you have 2 digits to the left of your decimal, it's not in scientific notation. Questions? Okay, let's use that and do an example. We want to write the following number in scientific notation. And our number that's a lot of zeros, right? There's 21 zeros, by the way. That
Yeah,
probably
I just
will.
think with 12. I don't like writing that many zeros. Keeps the point across the same as.
You're not going to have the right answer.
I can figure it out.
Okay, if you say so. So, where is my decimal to start with? It's right here, right? To get it into scientific notation, I need to move that decimal to the left until it's in which position?
Between 2 and 4.
Between the 2 and the 4. So I'll count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22 places. Okay?
13.
So our 10 will be raised to what power? The 22nd power. And what number do I put on the left? 2.4. Is 2.4 between 1 and 10? It is. Okay, let's do another example. I think we'll have time for both. Example 16. We want to convert to scientific notation. And this time our number's a little bit smaller. 36 million. So our decimal starts here. How many places do we need to move it? Well, we move 1, 2, 3, 4, 5, 6, 7, and put the decimal there. So we'll have 3.6 times 10 to the 7 power. Now this would work exactly the same way. If we had zeros in front of the decimal, you always want to have one digit to the left of the decimal in your final scientific notation. If you have to move the decimal to the right, you'll end up with a negative exponent. Any questions? All right, last example, and then I will let you leave. Example 17. We want to convert to standard notation. And our number is 3.547 times 10 to the 14th power. How do we do that? We need to move the decimal to the right 14 places. So 3.547. Every place that doesn't already have something there, we will add a 0. So we'll move it 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and 14. There's our decimal. And we'll fill in with zeros in every space that has a blank. So our final number is 354,000. No, sorry, 354,700,000,000,000,000, and our decimal. Now, are you going to be asked to do a number this big on your test? No, not at all. Okay, ladies and gentlemen, that is exponents and scientific notation. The end of section 1.2. Your homework is posted on Edfinity. Good luck on that, and I will see you tomorrow. Please let me know if you have any questions. Those of you in the co-rec will start at 9:30, and I will see you then.